All right, so welcome back, everybody. Sorry for the delay and sorry for the Wednesday class. So as I said, I want to quickly go over the topics that we covered in the class and would be part of your exam. Hopefully, this would be helpful for you guys to kind of also review. So my suggestion is try to kind of watch most of the videos first and then come back to this video and watch it as kind of like the last thing that you want to watch before the exam. This also helps you to, if you already watch all the videos and you want to kind of remind yourself of things, then I think this video would be a useful video. If you don't know anything about many of like if you there are you never watch some of those videos, some of the lectures, my suggestion is go back and actually watch them first because I'm not going to go through the details of each topic. I'm going to just go over the main concepts. Okay. So if you follow along in this class, the main kind of part of the class was teaching you advanced computer architecture, right? It's like giving you the details of like a modern system. And the modern system these days, as I said at the beginning of this class, is mainly out of order processors, superscalar, lots of things going on the processor side itself. And we also like talked a little bit about the memory subsystem because memory subsystem is also a very, very important aspects of any modern system these days. Uh, and then we mainly talked about the boom, the RISC-V base. So that was kind of like the major half, like in the first half of the class. We also talked about the security in computer architecture. So we didn't just talk about advanced topic. The security part is more of a researchy part. So it was kind of some introductory lectures by me, but most of the topics that we tried to target in the security part was based on the paper reviews and paper presentations. That's why I kind of I'm trying to push you guys to make sure to watch the recordings of those video, like those paper presentations as well. So make sure that you actually watch them before the exam on Wednesday. Uh, on the security side, we talked about 5 different important problems. The problem of side channels, obviously, we talked a lot about cache side channels as an example. But again, if you watch the paper presentations, you will see there's also other types of side channels. And of course, when we are talking about security, we talk both about the attacks and defenses. And then we moved on to transient execution attacks. The main 2 examples were Spectre and Meltdown. We also talked about Rowhammer vulnerability. And lastly, we talked about memory safety issues and trusted execution environments. Let me talk a little bit about the first half because it was kind of fairly long time ago. So if you remember, I said that essentially what we are doing is this stored program computers, where essentially you write a program, and this program becomes a sequence of instruction based on what a sort of standards that we have as instruction set assembly or ISA. In this class, we mainly focused on RISC-V ISA, but there's tons of other ISAs including x86 and ARM, which are the most popular ones. This ISA then usually translated into a binary, which is kind of like, sequence of zeros and ones, and then loaded into the memory, and kind of the memories is going back and forth between the memory and the CPU. And there's usually this register called program counter that kind of keep tracks of the program as it moves forward, right? That's kind of the general concept in any sort of modern system, let it be an in-order or an out-of-order or a single core or multi-core. Uh, Hopefully on Monday, we're going to talk a little bit about the database or data flow based systems as well that does not necessarily follow this stored program order concept, but almost all the modern CPUs following this format. In the designing the CPU, really what we care about is mostly performance, right? And the performance, the thing about the performance is really in decreasing the time it takes for the program to run. And we usually follow this quote unquote iron law of the processor performance, which essentially says that in order to reduce the time, we either need to reduce the instruction count, IC, or cycle per instruction, CPI, or the cycle time. In the class, we talked about each one, but really the job of the computer architect is really kind of like, improving this, the second one, this cycle per instruction. The other two is either the software developer slash compiler job, or the kind of the hardware designer, the real SI designer. So we really kind of like what we are trying to do is kind of reducing this as much as we can. But some of the techniques as a computer architect also impacts these other two. So it's not like, these things are not isolated. They're actually, relevant to each other. Then we started talking about an in-order design. This was kind of like a preliminary discussion that we had. And we talked about a bunch of different things. And this is kind of like what most of you have learned in, uh, uh, a basic computer architecture class. Give me a second, I'll be right back. All right, so I quickly pause the video, so let's continue. So as I said, this is what you've learned in your kind of classic computer architecture class, which we kind of designed a 5-stage pipeline, so on and so forth. And we discussed, basic things such as forwarding, stalling, branch prediction, data hazard. And it kind of like, we're gonna get this fairly busy design as what to do what and where to do different things. And if you remember, we talked about kind of every CPU design is essentially a combination of two things. The black part is kind of what we call the data path, and the blue part is mostly what we call the controller. Uh, so then we start talking about, okay, let's optimize this, and that's the birthplace of an out of order or modern computer architecture, and that's really what we try to discuss in this class. This more advanced things that we do in order to further improve the performance of a design, a baseline design like this. And we talked about various different ideas. These are classic ideas in computer architecture and generally in computer systems. Things such as parallelization, which essentially the idea is doing more things at the same time. Uh, uh, so pipelining was one, but there's tons of other things. Then we talked a lot about prediction and speculation, and as you've seen, that this is kind of the backbone of any modern CPU. And unfortunately, as later on in the class we talked about, this is also one of the key reasons that systems are not secure. And then we kind of talked about how to improve the prediction and speculation further. We talked about out of order execution, and we talked about making the memory also faster, because as we said in the class, it's not just all about CPU. You can make your CPU much faster, but at some point you're going to hit what we call the memory wall, which the memory becomes the bottleneck in your system. So we need to do all these sort of tricks, including the caching, the prefetching, prediction, and so on and so forth. Then we start talking specifically about a particular microarchitecture, a boom core, which was a RISC-V based out-of-order core. We picked this because this is kind of like an example of modern systems, a popular system. But essentially keep in mind that many of the things that we said in this class is actually being used in any other system, including like Intel and ARM processors, but there might be tiny differences as well. But we tried to kind of talk about mostly the approaches, the ways that one can do the various different things. And we talked specifically about the ways being done in the boom core. But as I said, there are other ways of implementing things as well. So if you remember, we said that essentially any sort of modern processors, out-of-order processors, has two, or the way we want to look at it could be three, main parts. The first part is the front end, which includes the fetching and decoding and renaming, which is kind of this top part here. Then we have what we call usually the back end or the execution unit, which has, the scheduling and the register read and actual execution and commit and so on and so forth. And then we have the interface with the memory, which is usually what we call the load store units, LSUs or LSQs. And then, of course, you have the memory interface in the background, which usually starts with L1 and L2 caches. But then, depending on the design, you might have multiple layers of cache, and then eventually the main memory. So let's actually go through these different parts one by one, as we did in the class as well. And this is kind of like the same example for a pipeline design in Boom Core. As you can see, it's kind of like has a fetch and then decode and rename, and then dispatch and issue, the register read, execute, memory stage, and the write back. And as you remember, we talked about various different parts in the system. Let's talk about the first four. That was kind of like what we call the backend. And again, essentially, originally, Boom was designed to be 10 stages, but really in practice, it's 7 stages because some of them are being combined. Um, and then we start talking about the front end, and we define what is the front end, essentially the fetch and decode. But then since this is an out of order processor, we also need what we call the rename, which I'm going to describe in a minute. The fetch and decode, of course, there are multiple different things that we discuss, including how do we fetch, what's the best way to fetch. We also talked about the caching mechanisms and what's the best way to cache instructions, because we are talking about instructions here, we're not talking about data. Then the big thing that we discussed and spent a lot of time was branch prediction, different types of branch prediction. And then we also talk about decoding and how to make the decoding faster. And of course, the key theme in all of these was similar to the other things that we discussed in this class, is how do we make things faster? Um, so as I said, there were like 3 main operations that one needs to be worried about in the front end. That includes the fetch unit, the decode unit, and the rename unit, right? So essentially, the goal of the fetch unit is kind of fetching lots of instructions and put it into some form of a buffer. And if you remember, we said that this is a superscalar processor, right? And the superscalar processor, since you want to run multiple instructions at the same time, then of course you need to be able to fetch multiple instructions, because if you can fetch and feed it into this buffer, then you can consume this buffer. If I cannot fetch enough instruction here, then of course this buffer is always half empty or fully empty, which means that doesn't matter how fancy my execution is. If I don't have enough instruction to execute, we're not gonna get enough performance. So fetching and putting things into this buffers was really important and part of a big part of any design. There are a whole bunch of problems with when it comes to the fetching and kind of feeding these instructions to the system, including the alignment issues, the branch prediction, and so on and so forth. So we discussed various different forms of things that we do in order to optimize. But then we also talked about, of course, decode and renaming, which I'm going to talk about in next few slides. Just to remind you about the fetch and generally the front end, we talked about various different versions of the Boom, but as I said in the class, we mainly focus on the newest version of Boom, Boom version 3, which fetch takes 4 cycles. The reason that it takes 4 cycles is that use a fairly involved branch predictor, has the PTB and the tag and the RAS. And then it has, the decoder and the dispatch, which each one takes only 1 cycle. And this is where we're going to actually kind of put things into the dispatch units, the instruction kind of queues. And this is where we're going to actually start issuing and scheduling things, which was part of what we call the backend of the process. So we discussed lots of kind of improvements and techniques. And as I said, I recommend you to go and watch the videos. This video is just kind of like here to, it's the purpose of this video is just giving you the pointers to this. So if you remember, we talked about how do we make the front end faster, and we talked about things such as we need a mechanism to fetch more instruction, but fetching more instruction itself excuse me, had lots of challenges. So we had to figure out ways to make this more efficient. Another thing that we could do is, improving the performance of the cache, in bringing more instructions, improve the usability of each instruction, and we define how does that work and what is the metric. And of course, the main things that you can do in the front end is having a better branch predictor to improve the accuracy and or the penalty. Um, and then we talked about, as I said, the main things in designing the system, including improving the cache itself, improving the locality, improving the number of useful instructions, and so on and so forth. This was mainly for the iCache optimization. Then we also, as I said, go through the details of the fetch unit, and as we described, there was 4 different stages, mainly because this backbone branch predictor was fairly involved and required multiple cycles. And most of you probably very well familiar with this branch predictors because it was part of one of your projects. Uh, and as you remember, we talked about various different things that we do in the branch predictor. We have this BTB here, which is kind of like just predicting the addresses. The BIM, the bimodal table, which kind of just saying that, predicting that whether the branch is taken or not taken. And this return stack buffer, which kind of like, just remember the return instructions, because if you remember, return instruction was slightly different than the rest, because you kind of can't remember what happens for a return instruction. And then, of course, the main thing was this kind of more advanced and complex branch predictor. And we talked about various different options here, including the G-share and TAG and so on and so forth. The main things for the branches really was that we need to predict the direction. And if you remember, not all the branches, not all the kind of control flow instructions have different directions. There are some of them that are always taken, including the regular jump instructions, but some of them are conditional, which means that they actually dynamically change. But then the second question that we also need to answer when it comes to the branch prediction is, what would be the address if the branch is really taken, right? So that needs to be something that we need to figure out. And if you remember again that another problem that we had was branch prediction caused alignment issues, specifically because when we are fetching multiple instructions at the same time, then if we kind of like jump, then some of these instructions would be not useful anymore. So we have to kind of figure that out and figure something in order to improve the performance. And then again, in order to design our branch predictors, we looked into different types of instructions, some of them conditional, some of them unconditional. There are some also specific instructions that we kind of like, specifically design something for them, including the call and return instructions. And then there's also this indirect branches that are really not performing very well when it comes to branch predictions. And we really didn't talk about the solutions for that. So yeah, and then we have a full lecture about the branch prediction. We talked about BTB, BIM, RAS, and BPD. And I definitely recommend you to go and watch that and look at your the project implementation, because we spend a lot of time on branch predictors. If you remember, we talked about this branch history table, which essentially what it does is has some form of a tag table to kind of understand which instruction is this. And then they had this simple 1 bit that decide whether the branch would be taken or not. And this bit is essentially the history. It's based on the previous behavior of that particular branch. And the BTB was essentially just finding the target address. It's a branch target buffer, which shows you which address this branch is going to jump into if it's going to be taken. So essentially, if the branch is taken, the address would be the address that is saved here. Otherwise, we just continue normally, which, for example, in this case would be PC plus 4. Then we start talking about, okay, 1 bit might not be enough. How do we make it even more interesting? And then we showed you a bunch of different things. One of them was, for example, having some form of hysteresis of 2-bit counters, but then say that, okay, only one 2-bit counter may not be enough. Then we need to have multiple of these 2-bit counters. But then the question would be, how do we actually define which one should we use? How do we select that? We talked about things such as having global history and having the PC and somehow combining them using some form of an XOR and then going through this table. And that was the idea of what we said, a G-share prediction. But then there was also some other predictions, and some of you actually use these other kind of flavors of G-share in your projects implementations. Of course, the main one that most of people use, and it's the most popular way of branch predictor, is take, which is kind of similar to this G-share in terms of there are multiple tables. The difference, though, is really the kind of like the big difference in take was this the way that we treat the history, which was based on some form of like, some mathematical series, and then we have a bunch of different type of history. Some of them, for example, is 2 bits, then 4-bit, then 8-bit, then 16 bits, and so on and so forth. And then we kind of like have this kind of a hierarchical way of predicting that what will happen, that if something happens in one and not the other, how do we update, and so on and so forth. So fairly involved design take, but it's also, I mean, in other words, it's also simple. So it's a very nice and interesting observation. And as we said in the class, this is kind of like the gold standard these days for branch predictors, because it's the right balance between the complexity and prediction accuracy. So that was kind of it for the fetch units. Then we also talk about other units, including the decoder. Decoder usually is n-wide, which means that if you fetch multiple instructions, of course you want to also decode bunch of them together. For example, for the boom, this was a 4-wide. We really didn't go through the decoder design because, as we said in the class, this is more of like a design of a you know, a finite state machine, an FSM. But we essentially said that what an FSM would do in this case is trying to figure out what sort of operation it needs to do, what sort of resources, what sort of operands. The big thing that we discussed was the renaming. And if you remember, the renaming is this unique phenomena that you need to have because you are moving instructions around, because you're running them out of order. As a result, you might introduce new type of dependencies, which if you had run it on a simple in-order machine, you wouldn't have it. But since we are running it in an out-of-order machine, we need to have it. So the trick was introducing this, what we call the physical registers, which was different than the architectural registers. And what we did was kind of like finding a mechanism to map the physical to architectural, and then kind of a mechanism to kind of propagating them, freeing them, allocating them, so on and so forth. But the big question was that since now we have these new kind of mapping, then we also need a mechanism to kind of revert things in case of a misprediction that happened or an exception that happened, and so on and so forth. So state maintenance was also like a big challenge when it comes to the renaming. If you remember, we talked about two main algorithms for renaming, the implicit and explicit. We talked about the trade-offs of each, and talked about what is the benefits and what is kind of like the problem in each of these scenarios. And we also talked about how Boom Core is actually implementing this. Um, so that was pretty much the backend. As I said, the backend is this part of the system that's kind of like start with the instruction cache and goes all the way to the beginning of the renaming. And that was the backend of the processor. Then we start talking about kind of the front. Sorry, this was the front end. Then we start talking about the backend, and the backend was the main things in the backend was that things are being executed out of order. So if you kind of compare a simple in-order machine and out-of-order machine, the front end pretty much the similar. You do the same fetch, decode, and kind of renaming if you need to. But really the backend is where things are different because you can execute things out of order. And then if you do the backend out of order, then we usually add this additional stage called the commit stage, which brings things back in order. Give me a second, I'll be right back. So uh, let's continue. Yeah, as I said, that there's this commit stage that we add in order to bring things back in order. So if you think about like the main steps that you would require in order to run things essentially out of order, we need to kind of create a buffer of unexecuted instruction. This is usually the reservation station or instruction queue. Then we need to kind of detect what is dependent to what. And then if you remember, there was this notion of capturing and waking up and selecting. So we discussed these various different algorithms and what we need to do for what will happen if you change that, so on and so forth. So it's pretty involved design, and there are a bunch of different design decisions that one needs to make. So definitely make sure to watch that lecture very, very carefully. Lots of interesting stuff there. If you remember, for example, we talked about dispatch, and we said that dispatching could be happening as a unified unit or per unit. And there were trade-offs there, including area reutilization, selection complexity, so on and so forth. Another thing was when we are issuing, what should we do? Should we read the registers and put them into the queue? Or should we just put the register names into the queue and then read them when we are actually executing them? And again, there was a bunch of different trade-offs there, including the register file designs, number of pins, the power consumption, the complexity of the issue, the complexity of waking up and forwarding, and so on and so forth. This is kind of like, showing that picture, showing that in a picture that you can either, put things explicitly into the reservation station, or not. And then the difference would be that the forwarding and waking up would be very, very different. Then we talk also about the execution unit itself, the functional units, the register file, the bypass network. This picture shows the actual implementation in Boom core, but of course, as I said multiple times, the exact implementation might differ from one processor to another processor, but typically we have something like this on the right, which you'll see that you have a bunch of different kind of banks. Each one is responsible for doing one particular operation. Some of them floating points, some of them multiply, divide, load, store, so on and so forth. We typically pipeline them to make them fast and allows the issue logic to issue multiple instructions at each cycle. And then again, we talked about the number of register files, things that we can read, and so on and so forth. Then the last thing kind of about the backend was the load store unit. There are tons of important issues in the load store unit, including the data dependence between consecutive requests. Then the requirement for kind of bypassing or skipping some of the more loads and forwarding them. We talked about the issue of disambiguation and ambiguation. And then we talked about the solution for the disambiguation, including speculative disambiguation. And we talked about what will happen if you make mistakes in disambiguation, if you're doing it speculatively. And generally, we talked about the memory bottleneck as one of the key issues. Again, here, there are lots of kind of design decisions that we made. We discussed the difference between them, what will happen if we do things at various different times. And I definitely recommend you to watch that kind of like part of the lecture very carefully, because there are lots of small details that we discuss in that lecture. So that was pretty much it for kind of like the design of the CPU, the front end, and the back end, including the execution unit and load store queue. So make sure to watch, the details. We probably in the exam not gonna ask you about the very, very details of the boom core itself, but we really want you to see if you have understood the kind of the design decisions and the trade-off between different options that we proposed. So what I would suggest to you is that you can always, like, since the exam will be open book, you can always like pick up the very tiny details of various different things, but try to understand why different decisions, what's the difference between the different design decisions, what are the pros and cons on each of one of them. So that's probably something you want to make sure that you've understood properly. So once we're done with, we covered the CPU part, we also talked a lot about the memory section of the CPU design. We talked about the memory hierarchy as a concept that, since the way that we design our memory, unfortunately, cannot give you both speed and area at the same time, we need to have kind of this multiple stages of the memory, which smaller gives you faster, but of course less storage, and then we gradually increase the size of the memory, but this means that also the latency goes up. Then we talked about the performance of the cache, and again, similar to kind of quote unquote the iron law, we also have similar iron law for cache performance, which was based on the hit time, miss rate, and miss penalty. We talked about lots of different techniques that one can use in order to improve each of these three different categories, the miss rates, things such as changing the block size and prefetching and the replacement policies and so on and so forth. The right buffer, sub blocking, and all those things, adding associativity, adding more levels, all those things for improving the hit time as well. So we talked about all those things, so I recommend you to kind of like look at them to learn about that. Another big thing that we spent a lot of time, one entire lecture, and your project was also on that, was the replacement policy. The replacement policy, the question was that we want to maximize the hit rate. We want to replace something with something else. What would be the right way to do that? And we talked about many, many different questions. Really, it boils down to three main questions. The first one was like which line to evict, right? So this was like the selection strategy that we talked about. The second one was like, now that we evict something and replace it with something else, where should we put this new line? And this was what we call the install. We talked about like least recently used, most recently used, somewhere between random and all those things, if you remember. And then lastly, we talked about what should we do if we see a hit. And this was kind of what we call the promotion strategy, that should be promoted all the way to the top or not, and so on and so forth. And as a result, we kind of like, talked about various different policies. We started with LRU, but then talked about the insertion policy, different types of insertion policy like lib and bib, and then dynamic one, which was dip. Then we talked about kind of the re-reference logic, that instead of using purely LRU, let's use something better. And that was the introduction of RIP. And then say that, okay, RIP itself also can have all these different kind of configuration, including the static RIP, which was strip, then the bimodal one, which was BRIP, and the dynamic one, which was DRIP. And then the reason that we want these is because of these different types of workload that we have in the system, right? So we have cache friendly, we have thrashing, we have streaming. So one needs to be able to kind of, look at these different types of workloads in order to be able to kind of design this dynamic systems. And again, probably in your in your project, you've seen how different data sets and different programs behave very differently. And then essentially most of these, systems that we talked about and probably you have implemented in your designs was based on this fundamental assumption that one can use this quote unquote hybrid method, where essentially instead of like choosing one specific method, they can choose two methods and dynamically decide which one to use. The main technique that we used was this thing called set dueling, which essentially we assign bunch of sets to one policy and another group of sets to another policy, and then decided which one is the best to do that. I again recommend you to go and see the details of those designs. And the last thing about the cache was sharing, because if you remember, we said that essentially most of these caches are shared among multiple cores. And what will happen is that these cores have different demands. So now the question is that if this cache here is kind of shared between these cores, how should we share them, right? Should we kind of say that, okay, each core should receive that, equal amount of memory to kind of ensure fairness? Or should we kind of say that, oh, everybody, it should be just free for all, whoever wants to use it, use it. And we talked about different kind of strategies and why one is better than the other, and kind of pros and cons of each of these two approaches. If you remember, we talked about this particular strategy called utility based. We define what is utility, how to track utility, and then based on utility, how should we actually partition the cache. So I recommend you to kind of like watch that lecture and follow that along. So that was kind of it for caches. We also then talked about memory subsystem as well, and the DRAM. And if you remember, I said that DRAM has this bunch of different kind of hierarchy. There was channels, and then DIMMs, and then rank, and then chip, and then bank, and rows. Um, which is kind of like showing you here as well that there's a memory controller that goes to the channel, and from the channel we go to the banks and ranks and rows. The big thing about DRAM was the scheduling policy that a bunch of different requests comes, which one should be service, and there were like different options that we had, that closing the row, opening the row, things like that. And then we talked about first come, first serve, first ready, first come, first serve, random, so on and so forth. And again, this was a particular project that you had, and still probably some of you are working on it. And you had to design kind of an algorithm that is both performant and power efficient in some cases. So that's the main thing about the design of that. So hopefully you probably have spent good amount of time on this, and now you've learned the differences between different scheduling algorithms. So that was pretty much it with all the advanced computer architecture part, but there's a whole bunch of security concepts that we also talked about. So we talked mainly about digital side channels, and we said that the main problem with digital side channels was that they break the isolation assumptions. And the reason that they break the isolation assumption was that they work on different contentions. So for example, we talked a lot about the cache side channels. We talked about how what we call the prime and probe works, and how the attacker can actually kind of like install their lines and then see what happens, and then kind of, based on that, predict what was the access patterns of the victim. But as we said in the class and in the paper presentations, cache is only one example. Unfortunately, any other microarchitecture unit can also be used in order for the contention to work. So again, this is where you have to watch the paper presentations to learn more about them. We also talked about the attacks and defenses for digital side channels, specifically cache side channels, how we can kind of change the programs and so on and so forth. Then we talked about transient execution attacks, and we said that this is another class of important attacks. And this is when it's kind of like, we form what we call a transient window, which could be because of the speculation, some form of speculation. And then we use some form of a channel, like, a cache side channel, in order to send the data out. Specifically, we talked about Spectre and Meltdown. If you remember, Spectre was when we put the code inside some form of an if condition, and then since we do prediction, we start this what we call the speculation window or transient window. And within that transient window, we could do things that we are not supposed to do. But then since the branch would be, for example, not taken, then it doesn't matter what we did, because we're not gonna get any error. But the interesting thing was that because of that actions, even though they're never really committed, they will impact the cache, and as a result, the adversary can actually go through the cache and recover that data as they wish. So there was again tons of different types of attacks. So this was kind of like a very simple observation, but there was attacks that actually shows that this could be taken to the next level, and there's a bunch of different ways that one can actually exploit this basic observation. And there were also some papers that we saw in the paper presentations about the defenses against these types of attacks. So watch them and make sure that you understand them. We also spent a lot of time talking about Brawlhammer as another vulnerability. This is more of like an analog based vulnerability because of the continuous kind of access to the nearby rows, and as a result, because of this nearby rows, the charge kind of go down at the point that it's actually flipping the bits from 1 to 0 or to 0 to 1. And we also, again, similar to this side channel attacks, we talked about different attacks and different defenses. And again, that's something you might want to watch the paper presentation to understand them. The innovative ways of attacking and innovative ways of detecting this attacks. And then lastly, we talked about memory safety and trusted execution environments. About memory safety, we kind of like go through this very detailed graph and talked about essentially what happens in most of these memory safety problems, that either you, as an attacker, someone would, exploit the temporal or spatial aspects of a pointer. As a result, they manage to write or read things from it. And as a result, they can do a bunch of different things, including modifying the code pointer, modifying the data variable, reading that data variable, and so on and so forth, which would result in various different attacks, family of attacks, including data-only attacks, control flow hijacking attacks, information leakage, and so on and so forth. Which some of you are already familiar with them, but there's also lots of specifics of that. We also talked about kind of solutions for this. If you remember, we talked about things such as CFI and memory tagging, and we talked about the difference between them and pros and cons of each one. And again, if you watch the paper presentations, you will see the differences and kind of like a more advanced version of each one of these. So again, I definitely recommend you to take a look at the presentations here, although the presentations here is slightly less than the others in terms of the number of papers, because it was just kind of toward the end of the class, so less people were there to present. And then lastly, we talked about trusted execution environments. And again, this is another kind of up and coming concept in computer architecture security, which essentially the idea is that let's have this trusted boundaries, because we kind of like need to understand that not everything about the system can be trusted. So how can we actually improve the system even under this untrusted system? And we specifically talked about one example of this, which was the RISC-V based implementation, that you can do different tricks, including cache partitioning, encryption, hardware encryption, software encryption, and so on and so forth. So again, I recommend you to take a look at this particular example and the two paper presentations regarding the trusted execution environments. All right, so that's pretty much it for the review. I definitely recommend you to watch all the lectures very carefully and the paper presentations. The exam itself would be on Wednesday in person. It would be open book, open notes, open laptop. This year, I'm gonna also try to see. I'm gonna test this and allow you guys to use any sort of it's LLM based, uh, assistants, including ChatGPT. Let's see how it goes. Maybe I will change my mind next time, but you guys are allowed to use ChatGPT as well. So let's see what happens. The test will be released on Gradescope, but you have to be there in person to kind of sign in a form. Probably gonna be multiple choices, true or false, some short answers, some long answer questions, and maybe some sort of like mathematical, questions as well. But mostly would be probably like, ask you to explain things, like the difference between this and that, and so on and so forth. I don't know the exact time yet, but it's probably gonna be about an hour to an hour and a half. We'll try to start around like 10 minutes after the beginning of the class and hopefully ends it by, 1.5 hour mark or close to 1 hour for 45 minutes. Everything in the lectures and the videos are included in the exam, but not the papers directly. So as I said, again, don't expect to me asking you like very detailed questions of this and that, but mostly about the concepts and the differences between different design decisions. And as I said again multiple times, you can actually watch the videos during the lectures. That's funny things that most people do it. So you can do it. Essentially, you're allowed to do anything you want during the exam, except of course sharing the answers and talking to each other, which is not allowed and considered cheating. But anything else is allowed in the exam. Okay. If you have further questions, feel free to post it on CampusWire. And sorry that this took a little bit longer than I was planning for, but hopefully it will be useful for you guys to watch it. On Monday, we're going to have our in-person lecture, which is going to be about, as I said, more advanced topics, which is not going to be part of the exam, but still, for those of you who are interested to learn more about computer architecture, that might be useful. All right, so if you have further questions, feel free to post it on CampusWire, and see you guys on Monday, or hopefully I'll see all of you on Wednesday. This is a rooster that I've seen in my recent trip. So thank you guys and have fun and see you soon.